Okay, so today we're going to work on the last example of displacement-based solutions, and I've saved this example to the very end because there are some tricks involved. And it's not a particularly hard example, but the assumptions involved are a little bit unique, and it makes our solution a little bit more tedious in some sense. Not in terms of mathematics, but in terms of making the right moves at the right time. So the problem, as all the other problems are, it's a pretty classical problem that you can find in old books as well. It's the thin spinning disk problem. Okay, so when you think of a thin spinning disk, think of, if you like, a CD-ROM, right? You put your disk or DVD or whatever inside the driver, and it rotates at a certain RPM, and that rotation causes stresses. And the radius of the DVD, for instance, is much smaller compared to, it's much larger than its thickness, so it is a thin disk which rotates at a certain high speed. So eventually we will see that this problem is a plane stress problem. The previous problem we solved was a plane strain problem. Pressurized cylindrical pressurized cylinder was a plane strain problem. This was a plane stress problem. There, the nature of the plane strain nature of the solution was not super important, but here the plane stress nature of the problem will be quite important at this stage. It will allow us to actually solve this problem. Okay. So just to give a simple schematic of the problem, so we have our disk. Okay. So it has a radius, let's say, A, and the thickness is T. And now we invoke, eventually, at some point we will invoke the thin disk assumption, which means that T is much, much less than A. So this is our z-axis. And the disk rotates with an angular velocity omega. Okay, so angular velocity omega, and it's a constant. Okay, so this disk, it's not accelerating towards some angular velocity. Okay, it has already accelerated, and now it is spinning at a certain angular velocity, let's say 1,000 RPM. And the RPM is fixed, and it's been spinning like that for a long time. So eventually that will also simplify our solution a little bit. Eventually in the homework, you will look at the case where it actually has an angular acceleration as well. You're able to also calculate a solution for that also. But here we're going to look at only the constant angular velocity case. So before I draw a little bit more, let's immediately remember the equilibrium equation, which says divergence sigma plus F equals rho u double dot. So usually in all the previous problems here, I would write F is equal to 0 and u double dot is equal to 0. That's the case we always looked at. So in this case, it's not a static problem. F is equal to 0. We will omit, let's say, gravity. But there's certainly an acceleration. So that is one way to look at the problem. And that's the way we are going to look at this problem. So the volume force is equal to 0. And all the components of the acceleration is equal to 0 except the radial one. The radial one, as we remember from dynamics, is simply minus omega squared r. Okay? And the acceleration is a constant. Now, on the other hand, so if you write the radial component of this equation, right, on the right-hand side, there is minus omega squared r. Another way to look at the problem, and if you would like to eventually, for instance, implement this in some software, another way to look at the problem is to say that actually u double dot is equal to 0, and the radial component of the volume force is equal to rho omega squared r. Okay? So all I've done is essentially the physical analysis reveals there's an acceleration, but I've taken it And I've said this is 0. Instead, I put that term to the left-hand side, and I've said that the radial component of the volume force is rho omega squared r. So these are two different ways to look at the same problem. So for instance, I'm going to show you some numerical problems. In that numerical setup, I have actually used this setup because it's, for me, easier. Okay? But when I do the analysis, I'm going to use this approach. But really, it doesn't matter. They are essentially equivalent, two equivalent views of the same thing. So now if I take this disk and I look at it from the top, there is another thing that we would like to simplify, a sort of a view of the problem. This is the center. And let's say there was I draw some line, right, on a portion of the disk, okay, at a certain radius. Now, what will happen is that under the action of rotation, right, this thing will try to expand, and this line will try to expand as well. Okay, so this line will move to a new position, and of course, I'm exaggerating, but it's going to move outwards like this. So now, the tricky part here is that if I look at any single point, for instance, if I look at this point, okay, even if this thing was not expanding, suppose it's not expanding appreciably, this thing is rotating at a very high velocity, right? So this point is going to keep moving around, okay? So there is, for sure, some sort of a tangential motion. But it's not a small motion. This is a very large rotation. It's a large, rigid body rotation, okay? But we know that rigid body rotations do not cause strains if they are small. In this case, it's not small, it's very large. So if I do my small deformation analysis, I will eventually get a strain out of it, which is not physical. It shouldn't be there. It's not compatible. The idea of a large rotation is not compatible with a small strain analysis, as you have noted in one of the homeworks. So instead, what I'm going to do is to eliminate that rigid body rotation, which physically I know that the inertia part is already in here. So this inertia due to rigid body rotation is going to cause stresses, and I'm capturing that. But the actual rotation of the points, I'm not interested in. So what I'm going to do is I'm only going to monitor the motion of lines or circular lines on this disk. What that means is that essentially we omit rigid body rotation of the disk, or so there would be a term, for instance, omega, that's the angular velocity, times t times radius. For instance, that would be the amount by which a certain point moves through a time t. I'm going to omit that, and I'm going to just look at how these lines expand. Another way to put this thing is I sit on the disk, okay, and I rotate with the disk. And with respect to me, the points move under the action of, let's say, centrifugal forces, whatever, that's what we used to call them in dynamics, right? They move, but I'm also rotating with the disk. So with respect to me, any motion is small because I share the large rotation of the disk. With respect to me, due to stresses, I will see the points moving a little bit away from me, right? Because the disk is expanding. But this way, I eliminate rigid body rotation. This is called small strain on large rotation. So the rotation is large, but the strains actually are small. Okay, that's essentially what I'm doing. Small strain with large rotation. Again, what is important is that the rotation is physically important, but I am capturing that through the angular acceleration, or the radial contribution to the acceleration. All right, so having said that, so now I have a setup, right? I don't have to worry about the rotation per se, but I have all the remaining parts of the physics complete. So I proceed with my usual displacement-based solution, and the starting point is always the displacement vector. So let's go ahead and write the displacement vector. So I have a UR, and as usual, I will write all the possible dependence of the components. And now, since I am sort of sitting on the disk and I see the points moving with respect to me, that motion will only be in the radial direction because the disk will only try to expand. The disk is not accelerating. If it were accelerating, with respect to me even, there could be a u theta, but it's not accelerating. So with respect to me, when I rotate with the disk, the points will just move away from me. So u theta will be 0. Now, on the other hand, the disk is expanding, and because it has some Poisson ratio, it will also try to contract because it will try to get thinner, right, for instance. So uz will for sure not be 0. So it's expanding, but also it's trying to get thinner, right? So uz is there, ur is there. Now, the problem has symmetry, so I can eliminate theta as usual, right? Now, this is where the problem starts to become a little bit tedious because it turns out that you cannot, in any straightforward manner, eliminate from the outset the dependence of, for instance, ur on z or uz on r. And I'm going to show you. It turns out that this is pretty much, at this stage, all we can do. Okay? And that's what, at the first sight, complicates this problem a little bit because we know that with our experience so far, we know that this problem can become quite tedious mathematically already. So we've already solved some problems. Remember, for instance, the torsion of a cylindrical bar. There we had some dependence of a variable. In fact, in that case, it was u theta, both on r and z, and that was already quite long. We had to do some separation of variables, etc. In this case, it's even, in some sense, dirtier. But let's stop at this stage, and I'll put an exclamation mark here. And I'll just say that this is all we can say at this stage. I don't want to simplify it further. So eventually, we will make some simplifications. But before that, what I'd like to get at is the stress. I would like to get the expression for the stress. And once we do that, I will go back to the computer, and I'll show you the nature of the solution, how it varies. And that will motivate some of the assumptions that we will eventually make. All right. So now, this is the view of the problem. And let me demonstrate, first of all, why there is an R and Z dependence. Again, we're going to view this in a numerical solution. But the reality of the deformation is, and this is true whether it is thin or thick. So what I'm going to draw it thick this to highlight the nature of the solution. But really, thin or thick, this more or less happens. So this is a side view. So what I'm doing is I am looking from the side, right? And I'm looking at towards the radial positive r direction, or the r direction, it's positive. And I take a cut, right? And this is what I see. Okay. By my construction, I'm going to assume that z equals 0 lies right in the middle of the disk. So this is the thickness, that's t, and therefore this is plus t over 2, and this is minus t over 2. So the disk, it's going to try to expand, and when it tries to expand, it will also try to get thinner, and you will see that eventually it takes such a deformed shape. So it's not an excellent drawing, but the point is it gets thinner here, and towards the end, it's a little bit thicker. So in other words, it contracts less at the edges. By way of analogy, right? So there are forces due to rotation. This is the center of the disk. It's the middle. Right? That's right in the middle. So if there is more material surrounding a point, those points will try to move and exert more, let's say, radial stress on this point, for instance. There's so much material surrounding it. So the stress, it turns out, at r equals 0, the radial stress, it turns out also the tangential stress, and we will eventually find these out, they are the highest. Okay? And because they are so high, they are trying to pull the material in the radial and the tangential direction. In the z direction, we'll talk about the stresses, but let us first agree that at the top, at this point, sigma z on the plane with normal z in the direction z, it's 0. Zr is also 0 because there are no tractions, right? It's traction free. And z theta is also 0. So z anything is equal to 0 on the top surface. And z anything, so that's what I mean by a dot, zr, z theta, zz, it's 0 also at the bottom surface. In the middle, it's not necessarily 0, in particular if it's thick, but even if it is thick, at the top and bottom, it's equal to 0. But so let's go back to my previous argument. So in the middle, r equals 0. It turns out the stresses, the radial and tangential, are high, so they are trying to pull the material in various directions, and it contracts in the z direction. Because the stresses are so high, it contracts most. As you move away from the center, like so for instance, over here, the material surrounding those points is just a tiny bit of material. So the inertia it experiences is much less, and therefore the stresses are less, and therefore it contracts less compared to that point. So that's why under the action of the rotation, the radial acceleration, this point contracts more, and these points contract less. Okay? But radial displacement-wise, this point is constrained from any radial displacement because it's in the middle, and by symmetry it's rotating about that point, whereas this point is the freest, so it goes outward most. Okay? And that's why it takes this shape. So now, therefore, if I were to draw a line initially on the disk, after deformation, it would probably look like this. And if I were to draw a horizontal line after deformation, it would probably look like this. Okay? So initially it was flat, and after deformation, it takes the shape of the red line. So now our second observation is that you see, so for instance, as I go in the radial direction, the amount of displacement in the z direction, it changes because this red line is curving up. Again, we're going to observe this. So which means that uz does depend on the radial direction. It also depends on the z direction, right? Because uz, by symmetry, along this black line, it's 0, right? Points above z equals 0 move down. Points below z equals 0, they move up, because the disk is getting thinner. Okay, but on this line, it's equal to 0. So for sure, there is a z dependence, and there is some symmetry about z, but the r dependence, because of this curvature of the line, it also cannot be omitted. And also, if I look here, right, I see that as I move in the z direction, the amount of radial displacement changes. If it had not, this line, initially it was straight. If there was no z dependence, eventually it would also remain straight. But it's not straight. Instead, it is curved like this. So which means that the radial displacement depends naturally on r, but certainly on z as well. Okay? So this is what we can presently say. Now, I can also see, by the way, that ur, right, it has this nice symmetry about z equals 0. Ur at plus z is equal to ur at minus z. If I'm at the same radial position, if I'm at a certain distance at the top, the radial displacement is the same as at a certain distance at the bottom, right? So there is a symmetry about z equals 0. Okay. And for uz, if you like, there's anti-symmetry, but I'm not going to worry about that. So that's the way the deformation looks. Again, we're going to observe that. So now, here's where our argument eventually comes in. So z is equal to sigma z, and any component, let's say sigma zz, okay? The normal stress on the plane with normal z. It's 0 at this point, thin or thick. That's the boundary condition. It's traction-free, and also here. Now we will keep making the disk thinner and thinner and thinner, eventually towards satisfying this assumption. Now, when you do that, the following will happen. there is a certain amount, an appreciable amount of radial stress and also a tangential stress. Those never vanish. And in fact, as you make it thinner and thinner and thinner, they converge to a certain limit, and that limit we are trying to capture with our solution. Now, sigma ZZ, for instance, it's 0 at the top. And if it's very thick, it has significant amount of distance over which, let's say, it can increase. Let's say, I don't know, perhaps it becomes compression. So it can increase, and then it can decrease back to 0. But if it is very, very thin, the distance is so small that it has to be 0 at the top, it has to be 0 at the bottom. And now, there is such a small distance over which it can grow that it can grow, but not to an appreciable amount. In other words, it turns out that it may be non-zero. Strictly speaking, it is non-zero, for instance, at z equals 0, but the amount will be very, very small compared to the radial and tangential stresses which dominate the solution. So in other words, eventually anything that has to do with z, sigma z, zz, zr, z theta, in the limit of a thin disk will be negligible. Okay? And we're going to neglect that, and hence we end up with a plane stress scenario. Okay? That's the definition of plane stress. So that's the argument. Okay? And I'll squeeze that in here. So sigma z equals 0 at z equals plus minus t over 2. This is true whether or not it is a thin disk. But if t indeed is much, much less than a, and in that case we have a thin disk, there is no sufficient distance for sigma z dot to grow to an appreciable amount. It does increase, but not to an appreciable amount. So we're going to assume that compared to the dominating stress components, which will be RR and theta theta, sigma z, sigma zr, and sigma c theta are 0, not only on the top and bottom surfaces, but they are going to be 0 everywhere. Okay? So this is our assumption. So I was trying to always consistently underline the major assumptions with a blue line. So previously it was sort of an AND effect or a Saint-Manon principle. In this case, it's a little bit different. It's involving the assumption of plane stress. Okay? So this is plane stress assumption. Okay, so good. Any questions so far? So we have the displacement. It's not super simple, but it is partially simplified. So let's go ahead and calculate the strain. So first, we calculate the displacement gradient. Again, I'm writing the only the components that remain. And so it's del UR, del R. We have a 0. There is going to be a del UR over del Z. Unfortunately, it remains there presently. We have a UR over R, a 0 over there. And here we have a UZ over del R, a 0 over here, and a del UZ over del Z. Okay, so that's our displacement gradient. And then we can calculate the strain. The strain is that plus is transpose over 2. So the diagonal, of course, remains as it is, del UR del R, UR over R, and del UZ over del Z. And this one is 0. This component, it's 1/2 del UR del Z plus del UZ over del R. And that one also is 0, and it is, of course, symmetric. Okay. Now, this one, just to simplify my writing a little bit, I'm going to call it directly epsilon ZZ. Okay, so because I have to take its derivatives and so on, so that one I will simplify a little bit in terms of notation. So then I proceed with the stress. right? That's the last step before we invoke equilibrium. So the stress is sigma lambda epsilon v identity plus 2 mu epsilon. And epsilon v is, I'll use also a simplified notation for partial derivatives. So it's ur comma r plus ur over r plus epsilon zz. That's epsilon v. And therefore, the stress is equal to, okay, right? So lambda that plus 2 mu this. So lambda plus 2 mu ur comma r plus lambda multiplying the remaining parts ur over r epsilon zz. That's sigma rr. And then sigma theta theta is lambda plus 2 mu second one, right? ur over r plus lambda ur comma r plus epsilon zz. And the last one is sigma zz, lambda plus 2 mu epsilon zz plus lambda ur comma r ur over r. Okay, and just to highlight, let's not forget, so okay, sigma r theta is equal to 0, sigma theta z is equal to 0. Sigma r theta is 0. I didn't assume anything specific apart from the symmetry. That's why it's 0. There is no theta dependence on any variable. Sigma theta z is 0 because of the plane stress assumption. But sigma zr or rz is, of course, not 0. It's 2 mu times that, or it's equal to mu times u r comma z plus u z comma r. Okay, and that's the stress. And of course, it's symmetric, just like the strain. All right. So this is the general expression for stress. So now sigma zr, sorry, z theta was 0 because actually not because of plane stress, but also because there is no theta dependence of any argument. But really, these components should also be 0 because of the plane stress scenario. So I did get some terms, right, because of the functional dependence, but this is sigma zr or rz. And due to my plane stress assumption, it has to be equal to 0. And this one is sigma zz. Again, due to my plane stress assumption, it has to be 0. Okay? And this one is 0, both due to plane stress, but also due to the fact that there is no theta dependence of my variables. So this is where I'm at now. Okay? So I did simplify the problem a little bit. I have some observations. I have some terms that I know need to be equal to 0 due to my plane stress assumption. But ur and uz depend on both r and z, which does not simplify my solution scheme appreciably at this stage. Okay? So at this point, I think it's a good time to stop and have a look at the solution of the problem. Okay, so that's our disk, right? Right, so these thin black lines are they indicate the original position. So it's pretty much conforming to my drawing, or my drawing conforms to this calculation. So it spreads, it gets thinner in the middle. That's where the stresses are eventually highest. And it's thicker at the sides. It contracts less. It does contract less. It turns out sigma rr at this point has to be equal to 0, by the way, right? So This plane, it's the plane with normal r, and this is the direction r. And it's traction-free. I'm not applying anything. So sigma rr needs to decay to 0. But it turns out sigma theta theta, so it's the stress on the normal to this plane, right, because that's theta direction. So it turns out it's not 0 even at the edge of the disk. So there is some tangential stress, and therefore it contracts even at the very edge of the disk, okay, compared to the initial configuration. And what we see here is the colors indicate sigma rr, the radial stress. And just for us, right, it decays to 0. Let's just try to remember this number. It is of the order of 4.5 10 to the minus 3. Okay? So that's the magnitude of the radial stresses. When I make it thinner, it will change a little bit, but eventually it has to converge to a certain limit. Okay? So now this is a thick disk. What you're seeing is actually half the disk, because this plane is z equals 0 plane. Okay, just like my drawing. So the thickness present is 0.9, so this is 0.45, half the thickness. The radius is 1. Okay? So 1 versus 0.9, that's an appreciable thickness. That's certainly not a thin disk. And therefore, if you look at, for instance, first of all, this is the radial displacement. Okay? The radial displacement, if it were only r dependence, right? Maybe it's not very easy to see. Let me look from far. Okay, it's more clear from far. There are these colors curve, right, like this. So which means that the radial displacement depends on the z direction, right? So z dependence of ur cannot be omitted, okay? And as I already noted, but this is a thick disk. Perhaps when it's thin, it might be omitted. Let's look at uz. And this is uz, right? uz, right? This point, so red means more displacement. It is negative because these points move down. This point is the symmetry plane z equals 0. It doesn't move anywhere. So it contracts here less. But you see, as I move along that direction, uz changes appreciably. So r dependence of uz can also not be omitted. But you can ask yourself, perhaps that is because it's thick. Perhaps it's thin. If it's thin, perhaps I can omit it and my solution will be simpler, right? Okay. Now, before I do that, let me look at the stresses as well. So the stresses, this is I cannot see it there. This is the ZZ component, sigma ZZ. So it's in the vertical direction, right? So the radial stress was of the order of 4.5, or let's say 5 10 to the minus 3. Here, the maximum value is, actually it turns out, it is compression, less than that. So almost, not quite, but an almost order of magnitude less. Okay? But still comparable. It's not super less. But it's thick. I don't expect it to vanish. So eventually, my assumption is that it should be 0. But currently, it's thick, but already less by an order of magnitude. And this quantity, it is sigma ZR. Okay? So on the plane with normal z in the radial direction, or on the plane with normal r in the z direction, whatever. So again, it's not 0, but it is less by 2 orders of magnitude almost. Now I see a 10 to the minus 5 instead of 10 to the minus 3 for radial. So it's already quite small, right? Okay, so there's the r and z dependence of ur and uz, and there are the z components of the stress, right? So far for a thick disk. So thick disk problem, it's not an easy problem. So now I will go and make the thickness, right? By the way, angular velocity was, in terms of RPM, it was 1,000, okay? And I will make the thickness 0.9. It was 0.9. I'll make it 0. Let's say 25. Okay? And I will go ahead and solve the problem once again. Now, what we are looking at is sigma RZ. It was like 10 to the minus 5. Now it decreased to 10 to the minus 6. If you look at sigma RR, okay, sigma RR is still 4.5 10 to the minus 3. As I said, it sort of remains over there. It converges to a limit, and that limit we are capturing. But so now, sigma ZR is 3 orders of magnitude less than this. So it's almost, it can be almost omitted. The thickness is 0.25 versus radius of 1. So the thin limit, as I said, it should be much, much less, right? It's much less, but in practice, that limit is reached quite rapidly. So the ratio present is just 1/4. OK, so we can look at also sigma ZZ. Sigma ZZ was before not that small. Now, when we look at that, it's also 2 orders of magnitude less than sigma RR. Now, that's fine. Eventually, so when I make it thin, they'll become smaller and smaller and smaller. So indeed, I can neglect them. That we believe, OK? But what I like to highlight is what I like to highlight is UR and UZ. Now, first, I'll begin with UZ. This is UZ. Okay? It's thinner now, but I pretty much see the same picture. In other words, there is, of course, some Z dependence of UZ, but there remains a strong R dependence. It doesn't seem like it's going somewhere. Like if these were just horizontal colored lines, then there would be only a Z dependence. But no, they curve up, which means there's an R dependence. So I'm not able to somehow get rid of that. And I can look at UR. OK, let's look at UR. And when I look at UR now, it's a little bit deceptive. When you look at UR, it seems that it only varies in the R direction. So it's almost like the Z dependence is vanishing. Okay? But that's because the disk is so thin, you don't see the slight variations in the Z direction. To make them more apparent, what I'm going to do is I am going to plot the gradient of UR with respect to Z. Okay? To show that UR changes in the Z direction. Okay? Because R dependence of Z was clear, but Z dependence of R perhaps is not so clear. So first, I am plotting the derivative of UR with respect to R, just to get an order of magnitude. So this is that term, UR, del UR, UR. And it's of the order of 10 to the minus 3 max, right? There is certainly a radial dependence. So now I'm going to look at URZ, that term. Okay. So URZ, it's it's 4 times 10 to the minus 4. It's just a little bit less. It's not even an order of magnitude less. So it's less, but although the disk is quite thin, it's not going anywhere. So we can also look at, for instance, UZZ. So UZZ is that term, just to get an order of magnitude. It's of the order of 2 times 10 to the minus 3. And now I can look at UZR to highlight the variation of Z with respect to R. 2 times 10 to the minus 3 versus something that is like maybe half of that, close to half of that. So it's not much less. It's still not even an order of magnitude. So when you look at the stresses, they are rapidly vanishing. But this radial dependence of UZ, so this term, and Z dependence of UR, it doesn't seem to vanish. And indeed now, if you look at this term, this is the term that vanishes. The individual components do not necessarily need to vanish. What matters is, in my assumption, this vanishes. Okay? So that's what we are. So in other words, we can't really omit this dependence, this complicated dependence of the displacement components on these coordinates. Okay? So we had to do something else. But let us proceed. So I have the stress. So having made some observations, I will proceed with the solution a little bit further. And so to close my loop in the displacement-based solution, now I will invoke equilibrium. I'm sorry, I closed the computer, but did you have any questions regarding that example? Anything? So we have divergence of sigma is rho u double dot, And let's go ahead and write that. with what we have. So in our setting, there is eventually, because there is a plane stress situation and there is no angular dependence of any component, the theta component and the z component of the divergence vector, they are 0 from the outset. We can omit them. And what only remains is the radial component. And we have written that several times before. It looks like this. Okay. Now, one difference, of course, from our previous cases is that these last two, of course, they're identically satisfied. This one is not equal to 0, but rather it's equal to minus rho omega squared r. Okay, so these are automatically satisfied, and this is the one that we need to now enforce. I have been very generous with my zeros. Let me narrow it down a little bit. Okay, so in the r direction, we need, right? Okay, that's equal to minus rho omega squared r. That's the term that I'm dealing with. This is sigma rr. So derivative with respect to r. So that's the first component. So lambda plus 2 mu u r comma, now two derivatives, right, rr, plus lambda multiplying first u r comma r over r, and then u r over r squared, and then epsilon zz with respect to r. So that is the del sigma rr over del r term. And then there is the 1 over r sigma rr minus theta theta. So that's classical. That's always 1 over r 2 mu, because epsilon v is in both of them. They cancel each other. So all I have left is 2 mu over r multiplying that minus that. Okay, so that is the stress. That is the r component of the left-hand side, and on the right-hand side, I have minus rho omega squared r. So as usual, we can do some grouping, and there is a typical lambda plus 2 mu factor that comes in such problems that we have also seen before due to cylindrical symmetry in this case. So we're going to have lambda plus 2 mu u r comma rr plus lambda and 2 mu. Let me write here just for a nicer view u r comma r. So we have lambda plus 2 mu, u r comma r over r is in both of them. And then lambda with a minus sign, 2 mu with a minus sign. So minus lambda plus 2 mu, u r over r squared. And finally, I have an epsilon zz r term, lambda epsilon zz comma r, and that's equal to minus rho omega squared r. And finally, I can divide everything by lambda plus 2 mu and multiply everything with r squared, just to get a nicer picture. So u r comma rr plus, so r squared u r comma rr, r u r comma r minus u r plus lambda over lambda plus 2 mu epsilon zz r is equal to minus 1 over lambda plus 2 mu rho omega squared r cubed. Sorry, I forget usually the r squared. There it is. Okay, so there is a UR, remember, it depends on both R and Z. So there's still some complication remaining there, but that's what we have so far. Now, the last thing you may recall is that this factor, lambda over lambda plus 2 mu, is 2 times the Poisson ratio. That's a identity that we used before. So I have a pretty compact expression, right? So, but there is a complication remaining so far. UR depends on both R and Z. And also there is an epsilon ZZR here. So there's a UZ component appearing in here. Epsilon ZZ is UZ comma Z, right? It's still there, right? So I cannot really get rid of that at this stage either. So now I go back here, okay? And I notice that since sigma ZZ must be equal to 0, I can express epsilon ZZ in terms of UR. Right? And that's what I'm going to do. I'm going to replace epsilon ZZ by using that. I'll go here, and I will simplify this equation to something that is only in terms of UR. UR still depends on Z, but at least my equation is only in terms of UR. So let's do that. So you have this equation written. It's pretty simple. Like epsilon ZZ is going to be minus lambda over lambda plus 2 mu times that due to sigma ZZ being 0. And I will write that now here. So because sigma ZZ is 0, epsilon ZZ, remember that's equal to UZZ, UZ comma Z, and that is equal to minus lambda over lambda plus 2 mu UR comma R plus UR over R. I will call this equation number 1, okay? At some point, we will need it. And notice that this is, again, 2 times the Poisson ratio. And what I'm trying to eventually get is I'm trying to replace this term, right? So I will multiply both sides with 2 Poisson ratio R squared, right? So, and I need a derivative also with respect to epsilon ZZ. With respect to R. So epsilon ZZ comma R, let's do that first, minus lambda lambda plus 2 mu. It's UR comma RR plus UR comma R over R minus UR over R squared. And now, just to get a similar term, I multiply with 2 times Poisson ratio times R squared. So 2 times Poisson ratio times R squared, epsilon ZZ over comma R is minus. So this, again, it's equal to 2 times Poisson ratio. That I can also simplify so that I get 4 times the Poisson ratio, right, times R squared. UR comma RR plus R UR comma R minus UR. So far, actually, aside from the plane stress assumption, we've done nothing fancy. It's just messy because of all that dependence of UZ on R and UR on Z. Okay? Apart from that, I'm just being careful. Following the steps, I've only invoked at this stage right here that sigma ZZ is equal to 0. That's all I've done. Okay, so now that term will be substituted in the equilibrium equation. So the equilibrium takes the form, right? So you see that there's a -4 Poisson ratio squared factor eventually multiplying every term that appears there. Okay, so there is a common factor, 1 minus 4 nu squared. If I group them together, right? For instance, multiplying r squared, the first term, ur comma rr, and then the second term as well, ur comma r, and then the last term as well, minus 1 minus 4 nu squared ur, and that's equal to minus 1 over lambda plus 2 mu rho omega squared r cubed. And of course, I'm going to divide through 1 minus nu squared. Okay. And that is pretty much what I end up with. Now, eventually, it's whether you like it or not, I don't know. But I like to simplify things when I can. But then, right there, it allowed me to simplify things so I could manipulate things easier. But then I end up with this. So I wonder if I take Poisson ratio equals this divided by 2, what would happen? If you do that, this expression looks a little bit simpler. So it's only in terms of lambda and mu. Sometimes that's nicer, so let's do that. So if you plug in the expression for Poisson ratio, then you get that result. And I'm going to call the whole thing here that this in fact, including the minus sign, right? Let's do that, including the minus sign. I'm going to call this a factor alpha. Okay? And so that this is equivalent to alpha r cubed. Because I don't want to drag it along as I try to solve the ODE. And I know what it is. It's something that depends on the material parameters and a problem parameter, which is the speed of rotation, angular velocity, omega. Okay? So the left-hand side is something that we now dearly know in cylindrical symmetry problems. If ur had a dependence of r on r only, then I could go ahead and immediately solve for it. There is one complication. This is not a homogeneous differential equation anymore. This equals not 0, but alpha r cubed. So there is going to be eventually a particular solution as well. But before we do that, let's look at the following. Again, ur is not something that depends on r alone. It has some z dependence. And for, let's say, to have a more solid approach, I'd like to eliminate that. Eventually, I want to have an ODE, something that, so presently it's a PDE because, strictly speaking, this thing depends on r and z, and I'm only taking derivatives with respect to r, right? But if I somehow could eliminate the z dependence of this variable, then it would be an ODE. It only depends on r, and derivatives are only with respect to r. So to do that, I'm going to play a trick, okay? So, and the trick is the following. And it is already slightly demonstrated here. the R displacement has a Z dependence, right? This is not the best picture because my disk is very, very thin. So because it's very thin, UR can change, right? UR can change, but just like the stresses, it cannot change appreciably. So the dependence and therefore UR comma Z remains appreciable in particular certain regions, but the change is small. It is there, but it's small, okay? So the arc of UR variation with Z, it's not as prominent as is shown here. It's there. So to eliminate that slight dependence, I'm going to average or integrate over the thickness direction and divide by the thickness direction. That is called thickness averaging. So to eliminate this small but certainly present dependence of that variable on the Z component, okay? And the motivation is that there's certainly a variation, and it turns out that I cannot quite omit it again. Why can't I omit it? I hate going back and forth, but I want to highlight, right? This is 0. This and that individually, they're not necessarily 0. In fact, they're sort of comparable magnitude to UR comma R and UZ comma Z. Okay, so I cannot omit that, but together they are 0. On the other hand, the variations, absolute variations of the variables, not the gradient, I'm going to eliminate that dependence by doing averaging over the thickness. So let me erase this as well and do that trick. Perhaps we could do something else. Perhaps we could, for instance, look at the relation between UR and UZ. Again, one last time, I want to pull this down. We could look at this equality. I say, oh, OK, well, there is some Z dependence of R and R dependence of Z, but such that they are equal to 0. And on that argument, perhaps I could simplify the possible dependence of R on Z and Z on R. I could do things like that, but I'm not going to. Based on the fact that the variations are small, but not necessarily the gradients, I'm going to introduce thickness averaging. So at this stage, and that stage is now our solution, which I can pull back up last time. This is our equation. And in that equation, UR is a function of R and Z. And we want to eliminate Z dependence. And as I said, we're going to introduce a thickness averaging idea. So UR dZ. I integrate UR over the thickness, divide by the thickness. Okay? And now I'm going to call it a variable that obviously, right, this depends on R and Z. I eliminate the Z direction. So now this is a variable that depends only on the radial direction. So this is our thickness averaged radial displacement. And if the disk is very thin, that should be a quite good representation of the radial displacement at every point. That's the idea. And you know, so one other reason I like this problem, okay, it's sort of messy up to a certain stage. The math brings you to a certain point, and then you have to say something. This is, I think, a slightly different presentation than what you can find in most books. But I like to sort of look at the problem in this way because this is a typical approach in different mechanics scenarios. For instance, if you want to deal with very thin structures, okay, this is a thin structure. For instance, a shell. Okay? Shells are what you build big stadium domes with, for instance, or eggshell. Right? In biology, your skull is sort of a shell. It's not quite thin-walled, luckily, but it's sort of a shell. So when the structure becomes very, very thin, typically at some point you do some thickness averaging. Another scenario is where you have two surfaces in between. You have a fluid, but the fluid domain is super thin. It's like your hands are wet and you're rubbing them against each other. So to analyze that problem, you could build a theory that is at some point based on averaging the fluid velocity over the thickness because the changes are not so, let's say, appreciable perhaps. Or you're not interested in the changes in the Z direction. You want to concentrate on the in-plane variations, okay, of the fluid. And that's actually a theory called lubrication. Which is under the field of tribology. But anyway, so this sort of an idea appears all over the place. So now once we do that, right, I have a variable. Now, if you look here now, and if I do thickness averaging on both sides. So first of all, The right-hand side depends only on r. So if I integrate over z, divide by t, I get the same term, right? It's a constant with respect to z, at least. And on the left-hand side, there is ur, yes, and there's other terms, but the derivatives are with respect to r, and all the factors are with respect to r. So when I do averaging, that averaging operation, for instance, the average of that is the average of ur with partial derivative with respect, or now absolute derivative with respect to r, because once you do thickness averaging, then z dependence disappears, and this becomes two ordinary derivatives multiplied by r squared. So this equation now becomes, which therefore, let's say, satisfies this thing, which is essentially now replaced, ur is replaced by capital U, and all partial derivatives become ordinary derivatives. So r squared u double prime, r u prime minus u is equal to alpha r cube. And now I'm happy, right? Because now this is a nice ordinary differential equation that I know how to deal with. And let us call this equation star. And because of the right-hand side, of course, it's inhomogeneous. Okay, but let's recall our ODE summary. When we were solving an ODE for the first time in the torsion of a cylindrical problem, and in fact, when we were looking at this radial part, we discussed this in detail. So, okay, second order, linear, non-constant coefficients, but the left-hand side we know how to deal with, and that's important because I know that if it's inhomogeneous, then the solution takes a homogeneous part, in other words, the solution with this omitted, plus a particular solution. And the homogeneous solution, I already know, and I don't need to do it all over again. UH is equal to some constant times R plus C2 over R. We'll solve it several times. And moreover, I know that R in my problem can go to 0 because it's a disk that is solid, that is spinning. It has no empty portion in the middle. If it did have an empty portion, so it was like if it were an annular disk, then R does not go to 0, so this term could be retained. Okay? But presently it can go to 0, so I omit that term. So the homogeneous solution has only one constant. And now there is a particular solution. The homogeneous solution has a free constant. This constant is determined by eventually boundary conditions. Again, remember from ODE theory that the particular solution has no free constants. And often, you find it by inspection. But there are certain reasonable approaches that one follows. And one of the reasonable approaches is, OK, so when I plug in UP in here, it has to satisfy that equals alpha r cubed. That's how you find the particular solution. And the idea is whenever you see a polynomial term, I look on the left-hand side, I see, right, two derivative, one derivative, no derivative, r squared. So I ask myself, if, and that's the solution in this case, if UP is a constant, and let's call that constant beta times r cubed, then this is r cubed term, r cubed term, r cubed term equals r cubed, so I could satisfy this equation. And if I could satisfy it, if this is a solution, this is the solution because it's linear. So then I go ahead and plug that. So it must satisfy star, which is our differential equation. And therefore, I have two derivatives. So 6 beta r cubed, one derivative plus 3 beta r cubed minus no derivative r cubed is equal to alpha r cubed, or beta is equal to alpha over 8. And there it is. And in fact, I know what alpha is. It was defined here. So let me write down what beta is. It's lambda plus 2 mu over 32 mu lambda plus mu. So hence our solution is, and I'd like to box that. So U is equal to some constant. I'm not going to write C1, just C is sufficient, plus a constant beta R cube. And that is the result. You want to take a break from our sort of, do you have any questions? Because it's been sort of intense in some sense. Right? I think we're doing fine. I mean, it's mostly math, as I said, but at some point you make a reasonable simplification. There are approaches that sort of invoke that the radial displacement depends only on R from the outset. But I think that's a bit of a messy view. I think this is a clearer picture of what is going on. Okay? Because if you omit the z dependence of UR from the outset, some of the physics you don't quite see because the z dependence is there actually. If you omit it, then the solution is much neater, it's quicker, but I think this way it's cleaner. Okay, and I think this assumption at some point, or this manipulation, it's not an assumption, it's just a manipulation that is reasonable based on the physics of the problem or the mechanics of the problem. It's important to sort of show it because it is something that appears often in different cases as well. Questions? Okay, so then we're pretty much done. Okay, so what I am going to do now is I would like to find this free constant C. Okay, the free constant C eventually goes into the stress components. I have some boundary conditions on the stress. And that boundary condition is on the stress is that the disk is rotating, okay? But on the outer surface, on the plane with normal R in the direction R, the disk is not subject to any traction, it's traction-free. So sigma RR at R equals A, the outer radius, should vanish. That is only a single condition. We only have one condition, but we only have one free parameter anyway. Beta is not a free parameter. It's a material parameter combined with omega, and I missed the omega. Let me write that. Rho omega squared, right? Should also be there. And in fact, I missed the minus sign as well in alpha. I'm sorry. So let's highlight this. Minus rho omega squared should also be there. Okay, so let's go ahead and find C. However, now I've done thickness averaging on U, so sigma R, because it depends directly on the UR variable, has both R and Z dependence in principle. So what I'm going to do is, I'm going to also apply thickness average to sigma R. Okay? I'm going to average it over to R. And when I do that, I will have a capital U instead of UR, a capital U instead of UR, and obviously I need to also thickness average epsilon ZZ. And I have an expression for epsilon ZZ that I derived earlier, and I called it equation number 1. So let me go ahead. First do thickness averaging on this, and then apply thickness averaging to that, and then impose a boundary condition. So first, I start with the strain, epsilon ZZ component. So I'd like to introduce a variable that is associated with epsilon ZZ integrated over DZ, and I'm going to call it capital epsilon, let's say, ZZ. And that is from equation 1. Okay, I already had written what equation 1 was, minus 2 nu u r comma r, now that becomes u prime, and then u r over r, which only becomes u over r because I do the averaging. And now I have an expression for u prime. I can go ahead and plug that in. It's equal to cr plus beta r cubed. So this is r plus 3 beta r squared plus ur over r is, sorry, this is c plus 3 beta r squared plus ur over r is c plus beta r squared. So 2c 4 beta or minus 4 nu c plus 2 beta r squared. Okay. So epsilon zz, average term, has that form. And then I can go ahead now, take the average of the stress, sigma rr component. I'm going to call it capital sigma, 1 over t. There is a capital sigma, by the way, but I think there is no capital epsilon, actually. But I called it capital epsilon anyway. So it fits nicely to this notation. So anyways, capital sigma is equal to lambda plus 2 mu. I'll just write it down because the expression remained on a different board. But averaging simply, instead of capital U, I had small ur, comma r, I had ur, and here small epsilon zz. After averaging, I simply replace them with their counterparts. And then I go ahead and plug in the form for u prime and ur and also epsilon zz. And that will give you a, okay? So let's do that. Why not? Let's do that step by step. U prime is c plus 3 beta r squared, okay? Plus lambda u over r, c plus beta r squared, plus epsilon zz, or minus 4 nu c plus 2 beta r squared. Okay? That's a direct substitution of what we have, just for completeness. And now there's a c term and there's a beta r squared term. I can collect them together. I collect the c's, I collect the beta r squareds. And with that, you would get sigma rr is let me know if I make a mistake at any point. I'm trying to check what I write, but if you have any remarks, let me know. Okay. And now we have our free parameter that we need to determine. And the way we determine it is we go back to the problem and we observe that sigma rr is equal to 0 at r equals a at any z. So this is the actual sigma rr. And since it's equal to 0 everywhere, for sure, its thickness averaged counterpart is also equal to 0. So all I have to do is go ahead, plug in r equals a in here, set it equal to 0, solve for c. Okay, that's it. So c is equal to minus this a squared divided by that. Now, that part is easy. Now, I have lambdas and mu's appearing everywhere, and together with the Poisson ratio, I will go back and substitute the expression for Poisson ratio in terms of lambda and mu. And if you do that, this expression will take a slightly shorter form, 7 lambda, 6 mu. Okay, so at this point, it's advantageous to do that because it's easier, right? And then I also remember that actually beta, just to give a glimpse of the complete expression for C, beta had a certain form. It was alpha over 8. Actually, alpha had a certain form. And if I plug in the expression for beta, it is, actually it's down here, right? I'm going to plug in that term. There's a minus sign, some bracket, rho omega squared. The minus sign cancels. So 1 bracket, second bracket, rho omega squared. Okay. Okay. That's C. Now we got it. Okay. I only have material parameters and omega appearing. And this completes our solution. Okay, so we've done it. I'm just going to take a few minutes more and highlight now what the solution looks like and some of the main features, and then we're done. So I have the expression for sigma RR here eventually, right? I'm going to take and plug C in here. Earlier, I had derived epsilon RR. We had an expression for sigma theta theta. So now I want to spare ourselves the effort of doing the manipulations. I'm just going to write down the final results for displacement and the 2 important terms, radial stress and the tangential stress, which dominate the solution. Okay? Those are actually the only stresses, right? There is no, right? When you look at the stress matrix, all the 3 diagonal components seem to be there, but sigma ZZ was 0, plane stress. Sigma RZ seemed to be 0, non-zero, but actually it is. We invoke it. So there was a term, but it was actually 0, right? The only thing that remains is RR and theta theta. So I'll write the expressions for those, and so we understand how the variations occur. So this is a summary of our solution. First of all, UR. Right? So we introduced it as a thickness averaged radial displacement. And that had the form CR plus beta R cubed. And eventually we found out what C was. And C has the form, or UR, therefore, has the form. I'll write it down. It's long, but the factors, of course, they're important quantitatively, but presently they are more important for me qualitatively. So for instance, if you look at this factor, right, in this, there is some factor, of course, it's positive, and then there's another factor here. It is also positive, and if you look, 7 is larger than 3, 6 is larger than 2, so this quantity here, it is larger than 1, okay? So if R is equal to 0, right? There is another R here. If R is equal to 0, UR is 0, and that's the center of the disk. Nothing can move, okay? I understand that. If R is equal to A, if this factor was less than 1, it would be negative. It would move inside. That wouldn't make sense. If it were 1, it would be 0. It wouldn't move at all. But this factor is larger than 1, so A squared times something larger than 1 minus a squared, so it's positive. So that point moves outwards. So I'm just checking whether my solution makes sense. It makes sense, okay? And I can move on because I could have made an error, right? So this tells me that u of a is greater than 0, for instance, just as a side remark, right? Simple way to check whether our solution makes sense or not. And then I can look at sigma RR, okay? And similarly, it was introduced as a average counterpart of sigma RR. And finally, I can look at sigma theta theta. Again, as the thickness becomes smaller and smaller, actually, right, these terms, the variation in those terms will become less and less. So they're almost a constant anyway. I introduced thickness averaging primarily for the displacement component because the dependence of that on z was not so clear. But in any case, I have these quantities which we have already calculated. The first one we have calculated. So it is 7 lambda, 6 mu over, okay, that's the simplified final expression, a minus r squared rho omega squared. That is sigma RR. Again, the solution at this point, I have a positive factor, and then the rest sort of matters qualitatively. At r equals 0, it's a maximum, and then it decreases to precisely 0. And because we have a boundary condition at r equals a, sigma RR should be 0. That was the condition we imposed. And now sigma theta theta, averaged over the thickness, it's 7 lambda 6 mu, 16 lambda plus mu, a squared minus some factor, multiplying rho omega squared. Again, from a qualitative perspective, positive factor, and then there's something else here. 7 is larger than 5. This is larger than 2. And so this is a factor that is less than 1, which means that, right, first of all, at r equals 0, it's a maximum, and then it decreases. And at r equals a, because this is less than 1, this is still positive. So sigma theta theta at r equals a is greater than 0. It doesn't go to 0. Okay? And that is why actually when we did the calculations, the thickness at the very edge still also decreased because there was something pulling the disk in the angular direction. Okay? And we can do a quick plot of the stress variations. This is the radial direction, and this is some stress component. Okay? And let's say this is r equals a. And sigma RR starts from a maximum and decreases to 0. Okay? That's sigma RR. And then we have sigma theta theta. When r is equal to 0, right? This term is not there. This term is also not there. If you look, if r is equal to 0, the factors at the front, they are the same. Sigma theta theta is equal to RR. So they start from the same value. But the difference is that sigma theta theta does not go to 0. And that is pretty much the end of the solution. And now when you look at that solution, what you see, of course, as we already discussed, the stresses are a maximum right at the center. So if you were to worry about whether your thin disk, whatever application you have, is going to fail or not, the point you should be concerned with is this point, right? Probably, okay? In particular, if it's brittle, let's say. And if it's brittle, then the normal stresses matter, and these are the normal stresses, so the maximum normal stress would determine failure. If it's ductile, you would have to look at von Mises criterion or some shear stresses in that case. Perhaps that's not the maximum point, most critical point, but that is at least one critical point to worry about depending on your material. Okay? Questions? Okay, so that was a long solution, but I think it was a nice solution, and now we're done. And next time, we are now going to move to stress-based solutions. So this was like the peak of our displacement-based approach, and we have seen how nasty this approach can be. There's a lot of involvement, and when the problem gets more and more complicated, the displacement-based approach almost becomes intractable. And therefore, we're going to pursue a different approach, and starting with next week. Okay, so thank you.